Hello everyone. So welcome to week 12 or the final live discussion session for the course Foundations of R Software. So we'll try to go through the contents of the last week, the final week's lectures, and also some content from week 11. Most of the discussion, or as a matter of fact, all of the discussion will revolve around the plotting functionalities in R. So, as always, I'll start by sharing my screen, and please let me know if I'm audible and if you can see the RStudio screen.
Yes, sir, you are audible and we do see this.
Very well. So, when you are working with large amounts of data, sometimes the best way to visualize the features of the data or interrelation between different pieces of the data is to do this graphically or visually. So that is where plots come into the picture, and plots show us the trends and characteristics within the data. Now there are various ways or various types of plots that you can draw, not only in R but for any kind of analysis. And R has a lot of inbuilt functionality that supports the construction of such plots as well as the customization of such plots. So the simplest plot is what is known as a scatter plot. So let's say we just have these 10 numbers from 1 to 10, and if I just say plot x, I'll get a graph like this. So now, since the discussion will be centered around plots, I am minimizing this sub window so that the code and the plots can be seen side by side. So if you're working in RStudio, you automatically have a space where plots will be presented to you. So just like you can have files, you can look at the packages, you can ask for help, you can have a dedicated window for plots. And as you resize this window, your plot will automatically get resized. So this is just an added feature for working in RStudio. And of course, if you want to look closer at some segment of the plot, you can always zoom in. If you want to store the plot as an image or as a PDF file, that is also allowed. And of course, you can also clear all the plots that you have made if you are not planning on storing them. Now, starting from a very simple plot, there are a few things that we can modify. So for example, so far this is nothing but a y equals to x kind of plot. So where the x-axis is just giving the order in which these elements of x appear. So here 1, 2, 3, 4 just means the first one, second one, third one, and so on. Now, the y-axis basically gives you the contents of x. We could have, just done, let's say, x times x. So you see, this is now more of a parabolic plot. You can, of course, wait. Now, as you make more and more plots, basically you can access the previous ones as well. And you can compare what changes have been implemented. And of course, if you want to clear a single plot, you just use this command. If you want to clear all of them, you use this. Now, starting from this simple plot of x, first thing we can do is maybe add some color to the plot. So that can be done using this simple argument called COL. If you say COL equals red, you see these dots become red, or we can make them blue. A few more things that we can do with the basic plot. We can give a title to the plot. So let's just say plot title. Now what else? We can also give the limits of the axis. Now this has to be given as a collection of two vectors, where the first one is the minimum value of the x-axis. So let's say I want this to start from 0 and go all the way up to 20. Similarly, I can do the same for y-axis, and this time let's say I'm starting from -2 and going up to 12. So this way you can make adjustments. You can also add labels. So let's just call the x label is the order in which the elements are appearing, and y label is basically the element itself. Now instead of x and index, it is displaying the text that you had provided. So this is the simplest example of a plot, but we can have more complicated stuff. So for example, let's say x, instead of being the sequence from 1 to 10, it's just a collection of categorical variables. Now, in today's class or in today's discussion, what we will do, of course, since we are demonstrating the plotting capabilities, will require data. So to build data, we will not explicitly just keep adding points manually. We'll try to automate this based on something that we have learned some time ago. So I want to reiterate functions. And one function which was very useful earlier was the sample function. So you give it a vector and it picks out elements of that vector. It picks out the number of elements you want it to pick out, and then you can store those elements into another vector, and then you can do operations on that vector. So for example, let's look at this one for a bit, and then we'll utilize it for our purposes. So I'll just call dice is sample, and I'll just say so 1, 2, 3, and I want to pick 7 times. And I must say replace equals true, otherwise. Okay, so does anyone remember why replace equals true is important in this case? Listen to the language very carefully. What sample does. So sample, you give it a vector, it will pick out an element of the vector, and then store that in this vector. Now you have a vector of length 3, you want to pick out 7 elements. And why is replace equals true important then? Anybody? So I'm picking from a vector. So what replace may mean in this context? What exactly am I replacing?
Sir, the element which is picked is replaced by.
Yeah, so if I don't set replace equals true, what will happen is, let's say out of 1 to 3, in the first, as the first number, let's say 2 is picked. Now if I don't say replace equals true, then that 2 is never returned to the vector. So the next entry will be picked out of 1 or 3. So if you want to extract more number of data from a vector of smaller size, you have to say replace equals true. So first time you pick up 2, and you put it back where you picked it from. So 1, 2, 3 stays 1, 2, 3. Next time you can pick 1, 2, 3. So your vector stays intact. So this vector does not break down. Otherwise, if I don't say replace equals true, you see, cannot take a sample larger than the population when replace equals false. So that's why this is important. So let's go back to this. So using this, what we have built is a dice which contains the elements of this vector, but in some arbitrary order, because this sampling is done at random. So let's make this a little larger. Let's say we want 50 elements. Let me clear the screen. So you see, dice is a sequence of 1, 2, 3, 1, 2, 3 in different order. Now if I just say plot dice, you see, this does not give me any useful information. I mean, this kind of a scatter plot, because all I can see from here is that, okay, the first element was 2, the second was 1, the third was 3, and so on. But it's not particularly useful. Now there was one command that we had seen last week, which is table. So what table does, if there is a repetition, or if there are repeated entries in a long list or a long container, it will just tell you, it will basically describe the contents of this entire thing. So dice contains 14 ones, 19 twos, and 17 threes. So if I plot a table of dice, you see, this is what I get. So the number on the x-axis basically gives me this particular entry. The number on the y-axis basically gives me how many times it occurs. So 1 occurs 14 times, 2 occurs 19 times, and 3 occurs 17 times. But a much better representation for this is something called a bar plot, because you can also think of the occurrences of these repeated numbers as the frequencies. So the frequency of 1 is 14, the frequency of 2 is 19, the frequency of 3 is 17. So we can also look at the relative frequencies. Let me just print this out. So now instead of the absolute number of times it appears, it's giving you the percentage of times it appears. So now moving on from simple scatter plots, let's look at a bar plot. So this is perhaps a structure that you have seen a lot in statistics-based text, and this is used to explain all kinds of data. So the difference between the relative and absolute is, graphically it's not particularly large. Now, the kind of customization that we had seen for simple scatter plots, these can be extended even further for the case of bar plots. So for example, now instead of giving a single color, you can give the color of, you can give different colors for each of the, something like this. Now let's see what happens if we give less number of colors. So this is the usual R behavior that we have seen many times. If you give it a vector with number of entries less than what is required, it starts repeating sometimes. So that is why if you give just a single color, everything will be of the same color. You can also specify a border. Let's say we want a red border. I know this may look a bit, jarring to the eye, so let's just make it black. what you can do is you can also give legends. So I think everyone is familiar with what a legend is in the context of a plot. So basically, a legend would describe, what each of this is describing. So for this example, we'll just call it 1, 2, and 3. And another thing that you can do is that you can maybe instead of having these vertical bars, you can also have horizontal bars. So you just have to set this argument equal to true. So this is effectively rotates the bar plot. So again, a lot of the plot customization becomes a matter of preference and also a matter of presentation. How do you want your data to look like? Now, bar plots are not just meant to describe data that is stored as vectors. It can also say something about data stored in matrices. So you can think of matrices having some columns and some rows. Each row may define a individual unit of data. Each column may define an individual feature of data. So let's build a matrix. I'll call it M1. So for data, let's see what are the variables that we have. We already have dice. So dice into x. Let me check. Okay, so it's size 50. So maybe what we'll do, we will make a 5 cross 10. We'll make a 5 cross 10, we can make a 25 cross 2, but okay. Well, let's just pick segment of this. So we'll pick 20 elements from this. So we'll define a matrix M1. My data is dice times x, and maybe I only pick the first 20 of these. Say n row equals 4, and call, or the other way around, n row equals 5, and call equals 4. Okay, we have to be careful sometimes, because if I had not added the parenthesis, the error was because it was trying to pick the 20 elements out of x, not dice into x. Okay, so you see some data in some order. It doesn't matter what this data represents, but let's try to make a plot. So we make a bar plot, and we enter the name of the matrix as the first argument. So let's just do that and see what appears. We'll customize it afterwards. So let me reproduce M1 again. As you can see, there are 4 bars, and each of them has been segmented into 5 pieces. So these 4 bars basically correspond to the 4 rows, and the individual segments within a bar corresponds to this entry. So this lower dark gray region, it corresponds to 2 on the y-axis. Good evening. Then afterwards we have 6 more, so that takes the total to 8. Then we have 3 more, becomes 11, and 12, 23, and 10, 33. So we land somewhere here. And now you can do a lot of things to customize this plot. So starting with the bar plot, let's say we add colors. Now, the way these colors will function is slightly different from what we had seen previously. So previously, when we made a bar plot using only a vector of data, and then when we were applying colors, entire bars were getting colored. So black corresponded to the first bar, blue corresponded to the second, green the third, and so on. But this time, since we are, sort of splitting my bars, and we are trying to describe different features of the same thing, so the segmentation and the coloration is also in the same manner. And you can give legends again. So let's just call it Monday. I'll call it MTW. Let's assume Thursday is a holiday. I need one more. So basically what's happening here is these legends, instead of defining individual bars, they define the segments within the bars. So any other information that you want to ask regarding simple scatter plots, and you want info for the exam and the assignments? You see, the conducting of these live discussion sessions and the conducting of the lectures by Professor Shalab and the examinations, these are separate things. So my responsibility is limited to organizing the weekly discussions and clarifying any doubts if you have. But in addition to that, if you have any doubts, you can always discuss on the forums. The primary material for the course are the lectures that Professor Shalab has uploaded. So all necessary examination related information is available through the NPTEL website, and whatever is necessary will be communicated or has been communicated to you by the NPTEL team. So I don't have any additional information to share with you, nor can I comment on what the contents of the exam will be or what the format of the exam will be. Other than that, so do you have any points that you want to ask or discuss regarding simple scatter plots and bar plots? If not, then I'll move on to the next class of plots. Okay, so let's move on to pie charts. So just like bar plots can highlight relative frequencies, a similar thing can be done with pie charts. So I add a dice, and I won't label anything. So you see, as you can see, simply drawing a pie chart for this dice variable doesn't help us very much. I mean, for comparison, let's make a bar plot of this. I think one of you is unmuted. Do you want to ask something, or is there a comment that you want to make?
Nothing, sir. Nothing, sir. I'm clear about it.
Okay.
Thank you, sir.
So as you can compare, if we look at the bar plot of just dice and the bar plot of the table of dice, you can see a clear difference, right? Because just a bar plot of this data treats the x-axis as the order, again in which the data has been collected, and the y-axis corresponds to the value. So this does not tell us much about the features or the frequencies. This only tells us that okay, the first element is 2, second element is 3, and that is not very descriptive. So what we usually want when we have categorical data like this, so 1, 2, 3 may correspond to some categories. It may correspond to customer reviews on a phone, on some app, or it could be just some numerical, translation of some abstract quantities. So much better information is provided from a plot like this, where we see how many ones, how many twos, and how many threes are there in this collection. So the same idea in mind, simply drawing a pie chart with a collection like this doesn't give me much information. So I just see, okay, what's the first element, what's the second element, and this keeps going counterclockwise. So a better way to, or a plot that can give us some more relevant information is the pie chart of the table of dice. So now you can see we have more cleaner segregation between data. So pie charts and bar plots can be used interchangeably. I mean, depending on your preference and depending on what kind of segmentation do you want to show. So for something like this, where we just have this 1, 2, 3, and we want to see sort of a percentage distribution, because here the angles, if you divide that angle by 360 degree, it gives you an estimate of sorts. Then a pie chart is better compared to a bar chart, because while it's conveying the same information, it's giving the number. The pie chart represents the proportions in a better way. Now, on the other hand, if you have data that can be segmented into different pieces, I mean, for each element you have some segments, then bar charts are more powerful. Now, sometimes maybe you want to represent two things side by side. So there are some global settings which can be set using this PAR command, which is you want to set some parameter for the graphics part of your code. This one, mf row, basically allows you to set the grid structure. So if you say mf row 2, 1, and then maybe plot this one, and then maybe plot this one. Maybe I should just use 1, 2, not 2, 1. Yeah, something like this. So it's possible to have multiple plots in a single figure, if you want to do this for comparison. So you don't have to look at different plots. I mean, again and again. I mean, in the same figure, you can have different components of the data described. Now, sometimes, especially when you have continuous data or the type of data which is not categorical, best example would be the marks of the student, but it's something that can be converted into categorical data, but let's forget about that part. So usually data that falls within a large range, and for that large range you can maybe define some sub ranges, and you want to see that for a given range how many elements fall within that bracket. So this is basically what can be achieved using histograms. So let's clean this up. Histograms are simply plotted using the hist command. And here let's put x times dice that we had done earlier. So now, okay, I should change the mf row parameter again. So now what is happening here? So x times dice, maybe we should just call it y. You see, it's a collection with the largest value being, I think, 30. Yeah, and the smallest value is 1. So the interval between 1 to 30, it can be split into many different pieces. Now, of course, at first glance, you may think that you don't have any control over, what's the size of the interval within which that R is selecting, but that's not true. There are arguments and there are parameters using which you can change this. So now, before going into that, let's see what exactly is represented by a histogram like this. So the question it asks is, okay, let's say the segmentation has been done. The size of the intervals has been set to 5. So the first question would be, how many elements fall within 0 to 5? So there's 1, there's 2, there's 3, there's 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And that's what this height of the histogram corresponds to. So that is the kind of information you can show. So speaking again of marks obtained by some students or a class full of students in a particular subject, that can be represented using histograms in a simple way that you can ask the question, how many students obtained marks in single digits? Then how many students obtained marks from 10 to 20, then 20 to 30. So you can set a segment size of 10 and then ask that how many students are getting what kind of marks in each interval. Maybe you can set a segment size of 20. So how many students between 80 to 100, 60 to 80, 40 to 60, 20 to 40, and 0 to 20. Now speaking of, again, what you can do with these plots, how to better describe the data. So of course, you choose the histogram and then you can maybe set a title. So this is describing marks obtained by some students. You can also set the color. So let's keep it. Let's make it blue. We can set xlim slightly beyond what's present so that my data looks more presentable. So maybe I'll set it from -1 to 31. Y-lim can be similarly set. So let's make it slightly larger, call it from 0 to 20, so that even the highest of my bars or can basically fall within my graph. Now there's this command of density. So density basically allows you to shade, instead of giving this solid rectangle, it can give you a shaded rectangle. So let's put density equals 3. Angle basically tells you what's the angle at which the lines that are being used for shading should appear. Let's call it 30. And the most important one is breaks. So how many breaks do you want between data? So that would be how many divisions are there. So in this case, the number of breaks is 1, 2, 3, 4, 5. So there are 5 breaks and it's fallen into 6 segments. So let's say we want this to fall into 10 segments, so I'll put 9 breaks in between. This is a little surprising. It's a little surprising why this is not exactly working. Let's try to store this in some variable. So okay, so looking at the doubt, okay, the question is what is C, A, comma, B. Basically this tells, this part of R, or basically the figure in which the plot is getting printed, how many plots can be added to a single figure and in what manner. So this whole white canvas, you can think of this as a figure, and in this figure there is only one plot. But if I say I want MF equals 1, 2, that would mean the figure will be divided into 1 row and 2 columns. So let's say I do this, and then I make this histogram, and let's go back a bit and make this bar plot. So this is basically what 1, 2 is doing. See, there is just 1 row but 2 columns. So sometimes you want to show a grid of diagrams, a combination of diagrams. So let's say, okay, this is something that will come a bit later, but sometimes you are working with data that may show some correlation. So for example, how much rain occurred in a calendar year, that may have some relation with what kind of crops were produced in that year, or what was the quality of the crops that was produced that year. So if you have an X variable that describes the quantity of rain, Y variable that defines the quantity of crops produced, And of course, there is some correlation between that. Or even simpler example. So, the cost of something, no, the total cost of a collection of objects is obviously related to the individual rates. So, now think in a situation where you have several different types of data. Let's say you have 4 different types of data and you want to study what kind of correlations exist between them. So then you make graphs, but taking 2 data sets at a time. So let's say your variables are x1, x2, x3, x4. You make one graph showing the relationship between x1 and x2. Another graph showing the relationship between x2 and x3. Then x3 and x4. Then again x1 and x4. Of course, you have more. You have 6 such relations. So you collect all of them and you want to show a comparison of these relations. You want to show everything side by side. In that case, this MF row is helpful. So if you have 6 different plots, but all of these plots basically correspond to the similar kind of information, then you can maybe set your grid or just the sectioning of your figure as 3, 2 or 2, 3, and you can have all of them in the same plot. So let's do something similar. So let's go back to the definition for dice. Let me clear this up. Let's say dice 1, just say sample. So from the sample of 1 to 4 maybe, we want to pick say 50 and then we'll say replace equals true. So this is dice 1. Dice 2, we do the same thing, but remember these are random samples, so we don't know and there is no guarantee that dice 1 and dice 2 will be the same. So if you look at dice 1 and dice 2, of course the ordering is different, and if I do their tables, that's also different. So number of 1s, number of 2s, 3s, 4s is different. So let me add 2 more. Let's say dice 3, and lastly dice 4. So now what I want to do, I want to plot pie charts representing, the frequencies of the different objects in each of these variables. So first I'll set this as 2, 2. Then I'll plot pi of the table of dice 1. Then I do the same thing for dice 2. So you see, what we had was a single source of data. Now, random variables are used to simulate a lot of real world phenomena. So a lot of things happen, let's say at the subatomic level, that we don't have any control of, or we don't know a deterministic way of predicting what will happen. So random variables provide a good approximation to what's happening there. So I'm looking at a single source and I'm reading what kind of data I'm getting. Now it's not necessary. So if there is some random process involved, it's not necessary that things will happen in the same order again and again. Things will happen in the same quantity again and again. So that's why I want to get an estimate. Each time I'm doing the experiment, what is the level by which these observations differ from each other, or what is the degree of randomness? So that can be done if I draw a plot like this, where basically I have a comparison of each of the 4 variables. So that's where this resetting the plot parameter and splitting the entire figure into separate graphs is helpful. So I hope that clarifies the doubt. What exactly MFRO does and why this is important.
Yes, sir. Thank you, sir.
Okay. Now coming back to histograms. Yeah. So I had stored the histogram, this one, in a variable called z. And from a histogram, if I just ask R to print the variable, or if I just call the variable, this basically prints a list, each of whose elements are named elements. And you can basically see what's stored here. So mids basically corresponds to the midpoint. X name is what's given here. Are these equidistant? That's true. What class it belongs to? It belongs to the class of histograms. What are the counts? So you can always access z and $counts, and it will give you the counts in each of these bins. So remember, for histograms, these individual rectangles are known as bins. Now, continuing on what I was saying about variables being correlated, or there being a relation between different variables, we can move on to 2D scatter plots or even 3D scatter plots, or we can look at bivariate data. What I mean by that, there could be relation. So we've all come across relations like this between 2 variables. So in mathematics, we write this as y is some function of x, and that function is defined as 2 times x plus 5. Now this, as you can see, is a linear graph. More complicated things could be something like maybe 3 times x square plus 2 times x plus 5. But this is obviously not linear. So linear is anything that is first order in x. The moment I add something of higher power, or maybe something of a lower power, or even something like this, I have moved away from linearity. I have entered the regime of non-linearity. So the functional relationship between 2 variables can be linear or non-linear. Now, there is another difference between 2 schools of, or maybe 2 big missions of statistics, descriptive and inferential. So in descriptive statistics, you are meant to describe data. So sometimes you know, what are the relations between different variables. In inferential statistics, the aim is to infer. You look at a set of data and you try to figure out what you can about the system. So in those cases, instead of having clean-cut relationships like this, you will just get a bunch of points for corresponding to one variable and another bunch of points corresponding to the other variable. And by looking at graphs, maybe we can get an estimate of if there is a good enough relationship or not. So I can give you one example to explore. Let's say in the game of cricket, I say my y is the number of runs needed. I have a fixed target, and y basically equals t minus x. So t is the target that has been set by the opposition team, and x is the current score. Now, can you tell me, is this a linear relation or a non-linear relation? Anybody?
The linear.
Linear, because the only power of x that appears here, and t is fixed, so the only way x influences y is through a single power, x to the power 1. There is no x square, x cube, 1 by x, sine x, cos x, exponential of x, none of that. But this is a linear relationship. Now, this is a fun exercise, or maybe something you can explore in your free time. I will not mention, what is the correct answer. Now, if I compute the number of runs needed using what is infamously known as the Duckworth-Lewis-Stein method, which often happens in cricket matches when there is rain or stoppage of play for some reason, then let's say the Duckworth-Lewis method depends on the current score and gives you how much more you need. Do you think this is a linear relationship or a non-linear relationship?
Non-linear.
Are you sure? This is a relation between the number of runs needed and the number of runs scored. The Duckworth-Lewis method depends on other variables as well. So, I won't tell the answer. Just for fun, you can try to explore. Whenever there is a multivariate relationship, so if I write just this means that there is a relationship between x and y. The moment I write this, it means there is some relationship between x, y, a and b. So these are 4 variables. These are related in some weird way. So it may happen that x is linearly related and a and b are non-linearly related. So this is something you can explore for fun. Okay. So to make the plots, we basically need data. Again, we'll take help of the functions that we had defined earlier. So just copy this. Or maybe this alone is fine. So let's say it's a randomly collected height weight sample. Now if you look at real data, that data may make sense, usually makes a lot of sense. There are patterns. But this one need not make much sense. So let's say we are looking at the heights of people within the range of 100 centimeter to 200 centimeter. We take 20 points, or 20 seems fine. Now we take weights in the same way. Well, let's say the weights of these people fall within 30 kilograms to 70 kilograms. Now if I just simply plot this, this is just an extension of the basic scatter plot function that we had seen at the very beginning. At that time we were only providing one argument, but we can improve this. We can provide 2 arguments. Let's say height weight. Maybe we set the x label as height, y label as weight, and let's see what we get. Should change the bar command again. So, based on this, do you think there is any correlation between height and weight for this randomly collected data? What is the normal expectation? Do we expect a shorter person to be heavier or a taller person to be lighter? Or do we loosely expect a sort of a linear relationship? I mean, as the height grows, weight grows. So if this had been real world data, these points may have fallen closer to a line. Now, there is another lesson that we should remember about data analysis. Sometimes it may happen that the data sample itself is corrupted. So, and you can see it very clearly. So, using random variables to map the height and weight separately is not a good idea. Because, okay, randomly you can choose some heights, but there is some correlation between height and weight. This we know from experience, this we know from theory. So, this is a poor approximation of the real world. That's why you have to be careful about the source of your data. Or maybe a plot like this can also help you judge the validity of your source. So, this is something that must be kept in mind. So with this, we'll move on to the last category of plots, which is 3D plots. Now 3D plots by default are not available in R or not in the base package. So we'll have to install a package called scatterplot 3D. And then we have to load them. Again, what I'm typing on the screen is something that we had encountered at the very beginning of the course, installing packages and using the library command to load those packages. Now you can see scatterplot 3D has appeared. So now if I just do a scatterplot of this, you basically get something like this. You can change this slightly. Even for simple scatter plots, you can just say, instead of points, you want some lines, or maybe lines connecting those points. Now anyways, this data did not reveal a lot of useful information. That's why even the 3D projection is not, particularly illuminating in any way. So a 3D plot or a surface plot makes more sense for more mathematical quantities. So let's say we already have x, right? Yeah, we already have x and we already have y. So let's try to see. So x we have y, just for to r is the square root. Or I'll just do this. Okay, y has more elements than x. So let's see if this will work. We basically have r, and as a function, we basically want, let's f be the function. This depends on r. Or actually we should have x and y both because we want a contour plot. So correspond sin r divided by r. This part I'll just copy and put inside the function. So it's a function. So outer is used to basically define the surface using x, y, and the function that acts on it. So as you can see, this basically leads to a grid of sorts. So a good way to visualize 3D plots is something called the perspective plot. Within the perspective plot, you give x, y, and z. And let's just keep it at that. Let's go. X is increasing for y. Let's replace it by 1 and 50. We should also add some angle, otherwise it's difficult to visualize. Basically, the idea is that you can see sort of surfaces here. So this surface is basically created using this function, and this is a 3D representation of this sin r by r, where the function depends on two variables. So z-axis basically gives you what that function looks like in 3D. Now, of course, you can always read more on the documentation of these functions and learn more about the different arguments that allow you to customize the plot further or to represent the information in different ways. And I think there are more options within the ggplot library, so you can always read on those and gain some familiarity. But ultimately, the use of plots depends on, what kind of data you're working with and how do you want to describe that data. Okay, so that was all on the last week's lecture materials. So hopefully this has been useful to you. If you have any more doubts, please feel free to ask. Okay, if not, then goodbye, and those of you who are appearing for exams, best wishes to you. This is the end of the course.